Today we are walking through the paper titled Qwen-AgentWorld Language World Models for General Agents.
What is the main question this work is trying to answer?
The paper asks whether a language model can learn to simulate the environments that agents act inside, instead of only training a policy that chooses the next action. That missing environment predictor matters because real environments are hard to scale. Terminals, search engines, mobile apps, browsers, and tool servers all have state, errors, schemas, and side effects that are expensive to reproduce at training time.
So the paper is not just making agents cheaper to train, right?
Right. The stronger claim is that simulation gives a different training access. A world model can create controlled failures, partial search results, or unusual terminal states, so an agent can practice cases that real environments rarely present. Here is the proposed model family. Qwen-AgentWorld is designed as one language world model for 7 agent environments: HMCP, Search, Terminal, Software Engineering, Android, Web, and Operating System Control.
What makes those 7 domains fit into one model?
The unifying trick is to represent every interaction as action and observation turns. A shell command returns terminal output. A tool call returns JSON. A tap on a phone screen returns the next UI state. Different environments become one next observation prediction task. The formal objective is simple. Given the prompt, the past observations.
Can you unpack the symbols before we move on?
The output is the predicted next observation. The prompt C describes the environment. The observation history tells the model what has already happened. The action history includes the current agent action. The equation is there to make environment simulation a direct training target. The examples make the task concrete. In software engineering, the model has to predict the Python traceback, including the memory allocation failure caused by the agent script.
That means the model has to understand the program state, not just copy terminal-looking text.
Exactly. The prediction depends on array shape, memory size. The world model is being judged on whether the simulated observation matches the real environment output. In the Android example, the action is a tap on by now. The model predicts a renderable HTML representation of the next screen, which becomes the checkout sheet.
So text-based and GUI settings both become next state prediction, but the state can look very different.
Yes, that is why the authors emphasize broad coverage. The same objective has to handle JSON tool responses, shell prompts, code errors, browser trees, mobile UI hierarchies, and desktop state. The training recipe has 3 stages. Continual pre-training injects broad world modeling knowledge for more than 10 million environment interaction trajectories. Supervised fine-tuning activates explicit next state reasoning. Reinforcement learning then sharpens fidelity with rubric and rule-based rewards.
Why do they need both rubric rewards and rule-based rewards?
The rubric reward can judge open-ended realism, actuality, consistency, format, and quality. The rule-based verifier gives a hard correctness anchor when executable checks exist. The paper combines them so the model can improve rich simulations without gaming loose natural language feedback. For evaluation, the authors built AgentWorld Bench from real environment interactions. It has 2170 turn-level samples across the same 7 domains, using ground truth observations from real execution.
What does the benchmark actually score?
Each predicted observation is compared with the real observation. The judge scores whether the format is valid. The facts are right. The state stays consistent. The response feels realistic. And important details are complete but not bloated. The headline result is that the large Qwen-AgentWorld model reaches the highest overall average, 58.71, ahead of GPT 5.4 at 58.25. Its advantage is clearest in text-based domains. Terminal improves over GPT 5.4 by about 4 points. And software engineering improves by about 2 points.
Does that mean it wins everywhere?
No. The paper is careful about that. On GUI domains, Quadopus and GPT models remain ahead, probably because multimodal pre-training gives them a stronger base for visual state. Qwen-AgentWorld is competitive there, but its main hedge is language-based environment simulation. The ablation is also important. At 397B scale, world model training raises the base checkpoint from 54.74 to 58.71. At 35B scale, it raises the score from 47.73 to 56.39, an 8.66-point gain.
How do they use the model after it becomes a simulator?
They test the users. In the decoupled setup, the world model acts as the environment for reinforcement learning. In the unified setup, world model training becomes a warm-up for the agent itself, so the agent learns to mentally predict consequences before acting. As a simulator, it improves agent training on OpenClaw-style tasks. With Qwen-AgentWorld as the simulated environment, Claw-Evil rises from 65.4 to 16.7, and Qwen-Claw Bench rises from 47.9 to 55.0.
What is the point of controlled simulation in those experiments?
Controlled simulation lets the world model create targeted pressure. For MCP, it can inject partial failures or paginated tool responses. For such, it can build fictional but self-consistent worlds where snippets reveal only part of the answer, forcing the agent to gather evidence across pages. The unified agent result says something different. World model warm-up transfers, even when the downstream task is multi-turn into using. The paper reports gains on out-of-distribution benchmarks such as Claw-Evil, Qwen-Claw Bench, and BFCLv4.
So the paper's final message is that predicting the environment helps both simulation and action selection.
Exactly. Qwen-AgentWorld is not presented as a complete solution to every agent environment. Certain GUI state are still hard, but the evidence supports the central claim. Language world models can simulate diverse agent environments, expose agents to controlled hard cases, and improve downstream agent behavior. That wraps up this paper walkthrough.